Okay, let's unpack this. Today, we're really focusing on, well, the mindset you need before you even think about building a model.
Right.
Talking exploratory data analysis, EDA, and why it's maybe less a set of tools and more a philosophy.
It absolutely is a foundational philosophy in data science. If you think about data life cycles, like CRISP-DM maybe,
Yeah.
EDA is right there in that initial data understanding bit. It's the essential detective work up front.
The historical definition is pretty simple, isn't it? Just looking at data to see what it seems to say.
Exactly. Keep it simple.
So the mission isn't just looking, it's looking beyond the surface appearances. Because, I mean, we tend to just look for stuff we already believe.
That's the trap, yeah. The whole point of EDA isn't confirming your hunches. It's about finding genuinely new insights.
Okay.
Focusing on what the data actually reveals may be challenging those assumptions you walked in with.
Which is why visualization is so central here.
Our sources really hammer this home. Its biggest value, it forces us to observe what we didn't expect to see.
Yeah, you need that forcing function. Otherwise, it's just confirmation bias playing out visually.
Precisely. Visual techniques are dominant because they empower the analyst, to explore openly. You have to let the data speak for itself, show its own structure.
And often that starts super simple.
Oh, yeah. The classics everyone reaches for first. Think histograms, box plots.
Standard toolkit.
They're practically mandatory early on because they instantly show you things like distribution shape, symmetry, skew.
And outliers.
And outliers, yeah, the stuff that could completely wreck a model later if you don't spot it.
Okay, so if EDE is this open-ended investigation, this exploration, we have to contrast it with what? The closing arguments. CDA.
Exactly. Confirmatory data analysis. And the distinction is, well, it's critical.
Why is that?
Because they are fundamentally different stages of inquiry. EDA is fast, it's qualitative, it's inherently subjective.
Subjective. How so?
It relies heavily on our human knack for seeing patterns, right? Forms, shapes, trends in the visuals. It's about generating hypotheses.
Okay, hypothesis generation.
Whereas CDA is the flip side. It's slower, objective, quantitative. It's strictly about verifying those hypotheses with statistical rigor.
Right. And mixing those up, I mean, using an exploratory chart as definitive proof, that sounds like a recipe for disaster.
It's the classic pitfall. There's a strong historical warning about this. If you don't keep these phases separate, you end up with what's been called crazy naive empiricism.
Crazy naive empiricism. Sounds bad.
It is. It's basically using data in a pseudoscientific way, just, cherry-picking visuals that seem to back up what you already believe.
Okay, give me an example, like an A/B test.
Perfect example. Say you're running an A/B test on a website change.
Right. And
you peek at the results early, and visually, it looks like your preferred version is winning. So you stop the test right there, declare victory.
But maybe it hasn't run long enough for statistical significance?
Exactly. You stop the moment your visual hunch, your exploratory findings seemed confirmed. You skipped the rigorous CDA step.
So I used a fast subjective tool, just looking, and treated it like slow, objective proof.
You got it. That's confusing the phases. EDA asks the questions. CDA demands the proof.
Okay, that makes sense. So let's focus on EDA's goals then. What are we actually trying to do in that exploratory phase?
Well, the aims are pretty broad, but also quite specific. You want to really maximize your understanding of the data set, full stop.
Which means?
Discovering the underlying structure, figuring out which variables actually matter, spotting those crucial outliers or anomalies.
And checking assumptions.
Yes. Verifying the assumptions you might be making about the data before you even try to build a model on it.
And all that groundwork, that's really in service of building better models down the line.
Absolutely. The endgame is often developing parsimonious models.
Parsimonious, meaning thrifty.
Yeah, simple, efficient models that don't use more variables than necessary, and also figuring out the optimal settings for whatever factors you're looking at.
Right. So the goals are complex, but getting started. The process itself can be fairly simple steps initially.
Very much so. It's visual and iterative. Step 1. Just plot the raw data.
Scatter plots, histograms.
Whatever gives you that first unfiltered look. Step 2. Plot simple statistics derived from the data.
Like means, standard deviations.
Or box plots, violin plots, which show those stats visually. Maybe a moving average if it's time series data.
Okay. And step 3 feels a bit different. It's about how you arrange things.
Exactly. It's about positioning these graphs strategically. Think matrix plots, dashboards, linked views.
Right.
To maximize your own pattern recognition ability. The real art here is translating your question like, Does failure rate jump when the temp goes over 80? Into a visual query.
Something you can see on a graph.
Right. And then interpreting the visual pattern, you see back into what we call graphic insight.
Okay, so what specific types of questions are we asking during EA? What are we hunting for?
We're hunting for structure, relationships, what kind of variations are affecting things, how are values distributed, are there correlations, trends?
So looking for connections between variables.
Definitely. But also looking within variables. What are the common values? What are the rare ones, the outliers? Are there distinct clusters or groups popping out?
And does stuff change if you look at subgroups?
Crucial question. How does a relationship between, say, variable A and B change if you only look at data from region X versus region Y?
Gotcha. Now let's get into the actual toolkit. The sources say the specific EDA techniques really depend on the type of problem you're tackling.
That's a key point. You don't use the same tools for everything.
They list 8 major types. Maybe we can group them. What's the simplest?
Probably the univariate problem. Just one column of data, y. Your basic model assumption is just y equals some constant value plus some random error. You're just trying to understand that single variable's properties.
Okay, one variable.
Yeah.
Then maybe checking if a process is stable.
Right, the control problem. Super important in manufacturing, finance. Is the system behaving predictably? Is it statistically in control or out of control? EDA, there's all about stability plots.
Then we get into comparing things or picking important factors.
Yeah, the comparative problem. Is the factor we changed actually significant? Is Group A truly different from Group B?
Okay.
And the selection problem. Using EDA to figure out which factors seem most influential and what their best settings might be, even before formal modeling. Sort of like initial screening.
Makes sense. Then the final group seems more about building predictive relationships.
Right. You've got optimization, finding the settings that maximize or minimize your outcome variable, y.
For basic prediction.
The classic regression problem. Using EDA to explore the relationship between y and various input factors. Is it linear? Curvy?
Yeah.
Does it need transformation? EDA helps you choose the right kind of prediction equation.
We also have data that unfolds over time.
Can't forget the time series problem. Y depends on time, maybe its own past values. EDA here is all about spotting trends, seasonality, cycles.
Okay, and the last one sounds like the big tangle.
The multivariate problem. Lots of variables, and maybe you don't even have a clear outcome variable defined yet. The goal is just to understand the overall correlation structure, how everything relates to everything else.
That structure makes sense. Let's maybe dive a bit deeper into that first one, the univariate problem. It sounds foundational, checking basic assumptions. The source mentions the 4-plot.
Ah, the 4-plot. Yes, it's a fantastic tool. Really efficient for checking 4 key assumptions about a single variable, all at once in a 2x2 grid.
Okay, walk us through the quadrants. What's the first check? Stability.
First is the run sequence plot. Data plotted in the order it was collected. You're looking for stability. Does it look basically flat? No obvious upward or downward drift?
And the spread.
And is the vertical spread, the variation, roughly constant over time? If yes to both, you've tentatively confirmed assumptions of fixed constant and fixed variation.
Okay, stable over time, then check for dynamic memory. Like, does the data depend on its immediate past?
That's the lag plot. You plot each data point against the one that came right before it. If the data is independent, uncorrelated with its past.
It should look like random noise.
Exactly. A formless cloud, no structure. If you see a line or a curve or any pattern, it means your data points are correlated, the assumption's violated.
Got it. Third plot, distribution shape.
The histogram gives you a quick visual sense of the distribution. Is it symmetric? Skewed left, skewed right. A bell shape suggests normality.
But suggests isn't confirms.
Right. For the definitive check on normality, which is a super common assumption in stats, you need the 4th plot, the normal probability plot.
And the visual cue there is?
A straight line. If the points fall closely along a diagonal straight line, your data is reasonably normally distributed.
And if not? If it curves?
If it makes an S shape or bows significantly, then nope, not normal. You'll need different techniques or maybe transform the data.
That's a really powerful 4-in-1 check. Okay, so that covers the basics. But what if my data isn't normal, and I suspect it follows some other distribution, like, say, y-bowl or gamma?
Good question. We still use a probability plot, but instead of comparing to a normal distribution, we compare it to the specific distribution we suspect, like y-bowl. Again, a straight line means a good fit.
But y-bowl, gamma, they have shape parameters? How do you find the best shape parameter? Trial and error sounds tedious.
It used to be. But now there's a smarter tool, the PPCC plot. Probability plot, correlation, coefficient plot.
PPCC plot. What's the magic there?
It basically automates finding the best shape parameter. Instead of you trying dozens of parameters and seeing which makes the probability plot look straightest.
It just tells you.
It plots the correlation coefficient, how straight the line is, against different values of the shape parameter. The peak of that plot shows you the optimal shape parameter value that gives the best fit for that distribution family. It's a huge time saver.
Okay, that's clever.
Yeah.
So we've tackled assumptions for one variable. Let's shift gears to that complex multivariate problem. No clear model, just lots of variables. How do we visually untangle that spaghetti?
Yeah, it can feel like spaghetti. We need plots that compress multiple dimensions. The star plot is one interesting way.
It's a star plot.
Each data point becomes a little star shape. The length of each ray or point of the star corresponds to the value of a different variable for that data point.
So you can visually compare the shapes of different data points.
Exactly. You can spot observations with similar profiles because their stars look alike. You can see outliers with weirdly shaped stars. You can sometimes see which variables are dominant because certain rays are consistently long or short across many stars.
Interesting. And for seeing all the pairwise relationships.
The workhorse there is the scatter plot matrix. It's a grid. Down the diagonal, you usually get histograms or density plots for each individual variable.
Yeah.
And then in all the off-diagonal squares, you get scatter plots showing the relationship between every possible pair of variables.
So you can quickly scan and see, okay, variable A and C look correlated, B and D, maybe not so much.
Precisely. It's often the very first thing you look at when you have multiple variables to get that high-level map of potential interactions.
Right. Now, we started by saying EDA is subjective, fast, hypothesis generating. But seeing a correlation in a scatter plot matrix, that's still a visual hunch, right? How do we make that leap to objective truth? Needs rigor.
Absolutely critical point. Because it is qualitative, because our eyes can play tricks or see patterns where none exist, we must follow up with formal CDA to counteract that confirmation bias we talked about.
So how do you rigorously test a hypothesis that came purely from looking at a graph? There's this procedure called the lineup.
Yes, the lineup protocol. It's a fascinating way to inject objectivity. It starts by treating your visual hypothesis, I think there's a pattern here, as false until proven otherwise.
Innocent until proven guilty for patterns.
Sort of. Step 1. You generate several data sets of pure random noise, null data, designed to look like what your data would look like if your hypothesis was false. No pattern present.
Okay, so a bunch of nothing happening plots.
Right. Then step 2, the lineup itself. You create a grid of plots, maybe 2 by 3 or 3 by 3. One of those plots is your real data, the one where you suspect a pattern. The others are filled with those null random plots.
And the key is the positions are randomized.
Randomized, and crucially, the analyst looking at the lineup does not know which plot contains the real data. This is called protective ignorance.
Blind testing for data visualization.
Exactly. The analyst's job is simple. Can you pick out the one plot that looks different, the one that doesn't look like random noise?
And if they can. If they consistently pick the real data out of the lineup.
Then the visual hypothesis is considered statistically confirmed. The pattern you saw wasn't just your imagination or random chance. It represents real structure in the data. It bridges that gap from subjective EDA insight to objective CDA validation.
That's a brilliant way to connect them. It really reinforces that EDA and descriptive stats belong in that early data understanding phase, making the map. While CDA and predictive or causal inference are for the later modeling phase, following the map rigorously.
You need both. The creativity and speed of EDA have to be checked by the objectivity of CDA before you build anything important on those findings.
So the big takeaway then, EDA isn't just plotting. It's this creative, visual hypothesis-generating engine. It lets us wonder, explore, question. But it absolutely must be followed by rigorous checks, like the lineup, so we don't just fool ourselves into seeing what we wanted to see all along.
Couldn't say it better. Its highest value really is forcing you to confront structures or patterns you didn't even know to look for.
Which leads to a final thought for you, the listener. Think about a data set you know well. What's an assumption you hold about it? Maybe that a key variable is normally distributed. Or that two factors aren't related.
What if you ran a quick 4 plot or a scatter plot matrix or a star plot on that data right now? Is it possible that a simple visual check would immediately challenge that assumption, forcing you to maybe set up a formal lineup to see if your belief actually holds water?